Hello again. This is the second part of the video on the last unit, which is ecology. And we're going to explain now the age structure diagrams for developed countries like in the United States. In the United States, for example, contrary to what has been found in the age structure diagram of Mexico, we can find that the majority of the population is not in the base. The majority of the population is in the age between 19 and 44. At the top, we have a smaller number of individuals than the intermediate age. And at the base, we do not have as many individuals as we have seen in Mexico. So here it's true that the old individuals represent a smaller percentage than the middle-aged individuals, yet the old individuals here, the total of their percentage is higher than the total of the percentage of old-aged people here, because here you might have a higher death rate, and that higher death rate is because of the poor hygiene or the lack of adequate health care in underdeveloped countries. How can we calculate the total percentage of individuals? You first determine the middle line, and then you determine whether you want to calculate the total number of individuals who are females or the total number of individuals who are males. So if you decide to do this for the females, so you'll find that in this age group, for example, you will have on the x-axis, it is about 2, and then we have another 2, for example, and then 1.5, and so on, and you add up the sum. So we measure the horizontal distance, and we compare it to the value on the x-axis, whereas the y-axis, or the values that are on the perpendicular axis, represent the age group, right? So here we have the percentage of the population that we are calculating, and here we have the age. Okay. So here we have a bigger total number of females in the age range from 50 to 80 and above. Similarly for males, and females are more if we compare them to people in Mexico. This is because of the increased health care. Meanwhile, if we compare this interval from 0 age to 14 to the age of puberty, we will find that the total number of individuals for the females, for example, and the total number of individuals for the males in those three intervals of age group are fewer than, or are smaller than, the ones in Mexico, and this is because of a lower birth rate. So at the bottom you have smaller values because you have a lower birth rate than in underdeveloped countries, and at the top you have a lower mortality rate. Okay, lower mortality rate. So it's no more pyramidal in shape because the base of the pyramid is now smaller in size. So this is what we call the zero population growth. Why do we call it the zero population growth? Because the values are almost stable. Since you don't have a big number of offspring at the bottom, then there wouldn't be an increase in the number of individuals, especially that the birth rate is almost equal to the death rate. They are both low in developed countries, and the birth rate is almost equal to the death rate, and therefore there is zero growth for the population. So whenever we say that a population has zero growth, then you have a death rate that is almost equal to the birth rate, and therefore there is almost a zero increase in the number of individuals in the population. Okay, so zero population growth is characteristic of developed nations. The population is stable. The birth rate, as we said, so what are the characteristics of zero population growth? we have a stability of the population. It is present in developed countries. The birth rate is almost equal to the death rate, and the number of people in each age interval or in each group is almost the same. Okay? These are the characteristics of developed countries and the age structure diagrams in developed countries. Moving forward to the next slides, we are going to see other age structure diagrams and compare them at the first look. So here, whenever you have, this is, for example, in Australia, in Canada, and in the United States, this is what we call the slow growth diagram. So here we have the purple indicates the age between 45 and 85. The gray indicates the age intervals between 15 and 44, and from 0 to 14, this is the blue color. So we have the rapid growth structure diagrams, the slow growth structure diagrams, and the zero growth structure diagrams. The main difference between the three structure diagrams is how we compare the birth rates to the death rates. In order for a population to have a rapid growth age structure diagram, then you should have the rate of birth, or the birth rate should be much higher than the death rate. Okay, so here, as you can see, the birth rate is high because at the bottom we have a very large base. So in the first age interval, for example, from 0 to 5 years old, we have like 7% of the population. In the slow growth, the birth rate will be higher than the death rate, but not as higher as in the rapid growth age structure diagrams. In the zero growth, we would have the birth rates almost equal to the death rates, and that makes sense because if every year, for example, you have 1,000 births, and similarly you have around 1,000 deaths, then there wouldn't be an ultimate or a net increase in the number of individuals in that population. You should be used to the general or the overall shape of the diagram. The rapid growth diagrams look like pyramids with pointed apices, whereas the zero growth have a smaller base and a wider top. Of course, in order to check whether the numbers are okay, you're going to add up all these. So you will find that the percentage is almost equal. Okay. Similarly, here we have the zero growth diagram where the birth rate, by definition, the birth rate is almost equal to the death rate. Okay. And we have the negative growth diagram where you have the birth rate smaller than the death rate. So the birth rate is smaller than the death rate. So if you have, for example, 1,000 births per year, then you might have 1,500 deaths per year, and therefore the size of the population is diminishing all the time. So you have a diminishing population, whereas here you have, when the birth rate is higher, then it is almost equal to the death rate. So you have an almost constant population, So in zero growth, you have an almost constant population, whereas in negative growth, you have a diminishing population in size. This is a diagram that shows you how the human population growth has changed over time. So we have the old stone age, we have the new stone age, we have the bronze age, we have the Iron Ages and the Middle Ages. So in this graph, what we focus upon is the red line that you see. So in the Old Stone Age, in the New Stone Age, in the Bronze Age, and in the Iron Ages, you can see that the human population wasn't even reaching a billion, because the unit here is billions. And then all of a sudden, you would have that in the more recent epochs, we had an exponential growth in the size of the population. Of course, here, for every period in the Old Stone Age, for example, you have the main characteristics of the population: hunters, gatherers, cave art, and then you have the agricultural revolution. But however, despite, for example, the presence of agriculture, yet the number of individuals all over the world did not increase tremendously, most probably because there were huge risks at that time, and there wasn't adequate, of course, knowledge about health and how to prevent diseases. So there were many people that died out of diseases or out of accidents. Of course, life was less secure and less safe than life is nowadays. And then we move on to the next slide, which is the biotic potential, I think, of the population growth. And we have what we call the biotic potential. What is the biotic potential? The biotic potential is one of the characteristics of a population, and it is the maximum rate at which the population could increase. Every population can increase at different rates over time, depending on many factors and depending upon the nature of the individuals or the genetic characteristics of the individual. So it's partly related to the genes of the species, of the individuals, and partly related to the environmental conditions. When the conditions are ideal and when the individuals are most fit to the environment, this, of course, would result in a high rate of reproduction or in a higher rate of reproduction. So the maximum rate at which a population could increase, and this, of course, would occur under ideal conditions, is called the biotic potential of the population. And as I said, the different populations will have different biotic potentials by nature, and they will have different biotic potentials according to the environment they are living in. Maybe, for example, they have a good biotic potential or a high biotic potential, but a catastrophic event, for example, occurs and leads to the death of the individuals. That's why we're talking about biotic potential under ideal conditions. In order for you to get the maximum rate, or in order actually for a population to get a maximum rate of growth, the population should be placed under ideal conditions. What are the factors in general that affect the biotic potential? We have four main factors that affect the biotic potential. The first one is the age at which reproduction begins. For example, in human beings, the age is a bit later than in other organisms because the couple have to prepare their home, they have to have enough money to be capable of making a family and be responsible for their offspring. But in animals, for example, it's a much earlier age, and the lower the organism is, the reproduction, the earlier the reproduction would start. Why is this important? Because if reproduction starts earlier, then the period during which the organism is fertile and can give rise to offspring will be longer. So we will have a longer period of fertility. So number one just equals a longer fertility period, a longer fertility period. And then the second factor that affects the biotic potential is the lifespan during which the organisms are capable of reproduction. In human beings, for example, that lifespan starts at puberty and ends at the menopause. So this is the lifespan. For example, for a female, this is the fertility period of the female. The longer this period between puberty and menopause, the higher the biotic potential of the population. So the smaller the age, when reproduction starts, the higher the biotic potential. So this is an inverse relationship, but the lifespan and biotic potential are directly related. Of course, it's meaningless to put this in number one and that in number two, because the age at which reproduction begins alone is not important unless you compare it to the age when reproduction stops, because it's this span that is more important. So I'd rather put them in one point, and the more important one is number two. The number of reproductive periods in the lifetime. For example, in human beings, it's a monthly process because the female produces an egg or an ovum every month. But if, of course, there are certain animals, for example, that produce the eggs twice a year only, then in such a case, the biotic potential, of course, of the population would be lower. So the more the number of reproductive periods in the lifetime, the higher the biotic potential of the population. For example, in bacteria, the life cycle is very short, it's a few minutes. So they have, of course, very high biotic potentials. But meanwhile, there are other factors, like, for example, the length of the life cycle, because they might produce a huge number of organisms, but they might be exposed to risks. The number of offspring the organism is capable of reproducing. There are certain animals that produce a small number of offspring. There are other animals that produce a large number of offspring. Of course, the larger the number of offspring that can be produced, the more the biotic potential of the population. So the characteristics of growth in a population, we first talked about biotic potential as a definition, and then we're going to talk about the characteristics of growth in a population. And these characteristics of growth are common to all populations, whether these populations have a small biotic potential or a large biotic potential. Now, the first characteristic is exponential growth. And of course, in order for you to get an exponential rate of growth, or a very steep rate of growth, positively steep rate of growth, there should be unrestrained growth, meaning that there are no restrictions for growth to occur. And this is the simplest model for population growth. And we are going to see whether this is a realistic model of population growth or not, because it's just like when we talked about Hardy-Weinberg principle that was talking about or describing stable populations. So in order for you to get an exponential graph that is very positively steep, having a very positively steep graph, then number one, the graph should be unrestricted. There should be no predation, just like I've just told you about bacteria. They have a very rapid rate of reproduction because they have a very short life cycle. However, they are exposed to risk, and they, although they have a very rapid rate of reproduction, yet they have a short life cycle. So population, or the organisms in a population, might reproduce rapidly, but they might be, like in fish, for example, but they might be exposed to great risks like predation, for example, or competition with other well-known organisms, or they might be exposed to parasitism, meaning that there are other organisms that might invade them and result in their death. In order, again, for exponential growth to occur, not only should growth be unrestricted, without predation, without competition, without parasitism, but also there shouldn't be any immigration or emigration, just like we said in Hardy-Weinberg principle, because if there is immigration, then the number will increase, but if there is emigration, then the number would decrease. Now, it occurs usually in environments where the resources are plentiful, where there is no competition for the resources. Actually, I'm not convinced with this point, because immigration will increase the numbers. So it should be no emigration. And this usually occurs in populations that have been recently introduced in an area. For example, if you introduce a drop of material containing bacteria on a guard gel or on a Petri dish, then the bacteria here are uncompeted, and since they have a very short mitotic cycle, they will divide very rapidly and produce a huge number of offspring. So this is a very good example. So you start, for example, by 1,000 bacteria, and you end up by having 10 to the power 9 bacteria in a very short period of time. And as I told you, this exponential growth is something that appears catchy, but at the same time, most organisms that reproduce that rapidly and produce a big number of offspring are short-lived. And therefore, with time, we might find that the rate becomes constant, or it might even decline because we have like a short-lived nature of those organisms. The human population has been in this exponential growth phase for over 300 years, growing rapidly, as we saw here in the diagram. This is the exponential phase. And then what happens after the exponential growth phase? That there will be limited resources. There will, even if there are no predators, there are no enemies, but the resources would become limited, and therefore some of them wouldn't find enough food or wouldn't find adequate shelters and homes, then they would die. So it's very logical that after the exponential phase, or in other words, it's very logical that the exponential phase cannot last for a long period of time, because it will be self-regulated by, for example, limited resources and limited space. So here we have two graphs. We have the exponential unrestricted growth, and we have the logistic or restricted growth. In the exponential growth, that cannot last for long, as we said, the growth rate of the population accelerates very rapidly. The rate of growth is very high. Here on the x-axis, we have time, and here on the y-axis, we have the population size. So if you calculate delta number, which is the population size, over delta t, which is the change in time, you would have a rate. And that rate is the rate of growth of the population, the rate of growth of the population. As we see, the graph is very steep, and this just means that the rate of growth is very high. And this simply means that delta m over delta t is very high. But as we said, this phase of exponential growth or unrestricted growth cannot last for long, because it will be self-limited afterward. And then we have the logistic or the restricted growth. After that period of steep growth of the population, where the rate accelerates, we reach a time when it's almost impossible for this very high rate to continue, especially when we reach the carrying capacity of the environment, the maximum number of individuals that the environment can hold. And we'll find that the rate will slow down, and we will reach a phase where we would have no increase in the population, meaning that delta n over delta t is 0. There is no change in the number of individuals as time passes, and maybe afterward you would have a negative slope of the curve, because the individuals are decreasing in number. So this is, whenever you see a graph like this, having time on the x-axis and having the population size n on the y-axis, then when you reach this stability phase or this plateau, then you reached a value that we call k. So this is the y-axis, and here we have a value that is called k, and k represents the carrying capacity of the population. In the other curve here, downward, you can see that we have the original carrying capacity of the population or the K value of the population. And then all of a sudden, because of limited resources or other factors, we find a negative slope and the population is decreasing until they get adapted to the new resources and we obtain a new carrying capacity. So there are some graphs where you have, for example, K1 that represents the old carrying capacity, and then you have K2 that represents the new carrying capacity. So what is the carrying capacity? As we said, ultimately, at the end of this exponential graph, you would find that you reach a maximum number of individuals that can be held in a particular area at a particular time. So you have to specify a particular area and you have to specify a particular time. And this limit will be called the carrying capacity K. Every environment has its own carrying capacity, absolutely, but at the same time, it also depends on the type of individuals that are living in that environment, because the environment has a certain, say, if we assume that the environment has a constant amount of resources, so these resources might be enough for population 1 to live for a year, for example, but if population 2 consists of bigger animals or animals that eat more grass, then the resources might be enough only for a shorter period of time. So it's true that every particular environment has its own carrying capacity, but it's also related to the type of individuals that are living in that environment. Usually when the population reaches the carrying capacity, we have a more or less constant number of individuals, but it's oscillating, meaning that there might be slight changes up or slight changes down. And that carrying capacity, as we said in the second graph at the bottom on the previous slide, there might be a new carrying capacity when the environmental changes occur. For example, a catastrophic event like a fire, for example, that destroys the trees in a forest. So if you're ever asked about the cause of that like rapid negative slope of the population, you might talk about natural disasters. Natural disasters like earthquakes, like volcanoes, like fires, for example, that destroy the natural resources in an environment. And then we have other characteristics of individuals like the R strategists and the K strategists. Here we have the rate of increase of the population. We are going to look at the first about the characteristics of population growth, and then we will be seeing what our strategists are or case strategists are. And since we have the slide in front of us, then let's first discuss it. So the R strategists and the case strategists are two different types of individuals or two broad categories of individuals, and we classify them according to their growth patterns. The R strategists are usually opportunistic individuals, meaning that they seize the opportunity when the environment is uncrowded, when they are introduced, for example, in a new environment and the resources are fast. For example, sometimes when you have a catastrophic event like a huge fire, for example, and many organisms are destroyed. So here we will have very few organisms that are left. At that time, the opportunistics will, if they are already present in the place, they would find it a very an amazing opportunity for them to reproduce and grow uncompeted. Since they are uncompeted, then there would be an extremely rapid rate of growth, an extremely rapid rate of growth. Okay. Of course, if there is a catastrophe, then these organisms would be capable of living. For example, if there is a fire that destroys the forest, you might be wondering how these organisms can live. For example, if all the trees have been destroyed. Yes, the destruction of all these trees have prevented regular animals, for example, from living in the forest, but if we have lower organisms like fungi, for example, they might proliferate in that area, or other organisms that are usually weak, that are usually incapable of competition, but when they find themselves uncompeted and they have their own resources that are not plentiful, but they are suitable to them, then they will flourish. But sometimes when an organism is introduced in a new community where there is no competitors, then at that time there would be resources if there hasn't been a catastrophe or a risky event that occurred before their introduction. On the other hand, the case strategists are more or less constant in their rate of growth, and they live at a density that is near their carrying capacity. The R strategists develop rapidly, and then they might continue on a certain carrying capacity, or they might disappear. But the K strategists from the very beginning live towards their carrying capacity. Okay, so here these are the R strategists. As you see, they flourish and proliferate rapidly, but they might disappear rapidly for a reason or another. Whereas the K, they look like a spike in the environment. But the K strategists from the very beginning, they're more or less towards the carrying capacity. Of course, this is the growth phase. And then we have the K, or the carrying capacity, and they are almost throughout their life, they are around the carrying capacity. The same applies for this graph. So if you have these two curves, then definitely, since you have an exponential growth, then this represents the R strategists, whereas this one will represent the K strategists. Why did we call them K strategists? Because they live more or less around their carrying capacity, meaning that in the R strategist, the population increases rapidly and then decreases. In the K strategist, the population grows rather more slowly and then stays constant in number in a particular area at a particular time. When we talk about R strategists or K strategists, we talk about a particular environment or a particular area and during a particular period of time. We cannot leave it open. We have to specify the area and we have to specify the time. I'll not be repeating the Lynx and Hare oscillation model because we have mentioned it before, but it's just the oscillation around the carrying capacity for each of them. What are the limiting factors that might limit the population growth? There are density-dependent factors. Of course, the population growth factors, when we talk about limiting factors, then we talk about the factors that restrict population growth. We don't talk about factors that favor population growth. So what are the limiting factors for population growth? There are two broad categories of factors. We have the density-dependent factors and the density-independent factors. The density-dependent factors means that it's a self-limiting process. For example, as I told you before, if there is an exponential rate of growth and then there are too many organisms for the place or for the resources that are available in the place, then there would be competition for food. There wouldn't be enough food for all the organisms that are present, or they might be competition for space. There wouldn't be enough space for all the organisms, or they might be buildup of waste. Notice that in the world of animals, there is difficulty getting rid of waste. So the buildup of waste might interfere with the rate of reproduction because of the space, or it might interfere with the rate of reproduction because of diseases and bacteria that might flourish in the space. Density-dependent factors is also predation, because the more the organism is, the greater the number, the greater the likelihood that this organism will be the search image for the predators, just like we mentioned before in evolution, and then the presence of diseases, because the more the number, or the greater the number of individuals, the greater the likelihood of occurrence of diseases. So how are these factors related? The higher the density, the more the competition for food, and the lower the population growth. Similarly, the higher the density, the more the buildup of waste, and the lower the rate of population growth. So you have to be very focused when you're asked about the relationship. Is it the relationship between the factor and between the density, or between the factor and the rate of growth of the population? The more the density, the greater the predation likelihood, and the more the density, the greater the occurrence of diseases, and therefore the diminution of the size of the population. So all these factors, competition for food, buildup of waste, predation, and diseases, are directly related to density, and they are inversely related to the population growth. There are other factors that limit the growth of the population, but that are not related to the density of that population, like earthquakes, for example, storms, naturally occurring disasters like fires or floods, that will drastically diminish the number of the population, and it's totally unrelated to the density of the population. Here we can find like a focused comparison between R strategists and K strategists. The R strategists grow rapidly and drop rapidly. So the growth rate is very high. So at the beginning, we might find many young individuals, but because there is little or no parenting, then they will die rapidly, and then they will drop again rapidly. They reach maturity early. And we said that the earlier you reach maturity, the longer or the higher the reproductive capacity of this population. But it all depends, from my point of view, not only on when you reach maturity, but about the interval between reaching maturity and being immature or infertile at the end, or dying. Because even if you reach maturity early, but you die early, then the interval would be short. They reproduce once, usually, for example, like one cycle, and then they die, because one cycle makes them big in number, and then they reproduce rapidly, and then they have problems continuing. For example, the insects, for example. So the insects lay their eggs, and then they lay the eggs once, and then the eggs hatch and give another generation of insects, and usually the insect dies afterward. And then we have the K strategists that have fewer. Of course, the prototype of our strategists, for example, are the insects and the fish, but the prototype of the K strategists are humans. So they have fewer young people, of course, than or individuals. They have intensive parenting, slower maturation, larger individuals. They reproduce many times during their life, and we have mammals in general as an example. Okay, here we have the story of the hare and the lynx, and it is a perfect study for population growth. And we have explained in evolution that there are fluctuations in the size of the population for both animals. The hare feeds on grass, and the lynx feeds on the hare. So the cycles in the lynx population are probably caused by the cyclical fluctuation of the hare population. So when the lynx eats a lot of hare, then the number will diminish, and the number of lynx will diminish accordingly. But there are other factors that might affect this, other than the hare being eaten by or predated by the lynx. For example, they might be overcrowding from the hare, so there would be competition for food, and there would be malnutrition because of overcrowding, or they might be overgrazing by those types of rabbits or overpredation by the lynx. So the drop in the size, in the population size, of the hare might have three main causes: either malnutrition from overcrowding, or overgrazing by those hare animals, or overpredation by the lynx. But anyways, once the hare drops, then the lynx will drop afterwards, but it would be shifted a bit later. Okay, we will stop here and then we will have another section for the video. Thank you.